you're like, where can I find this lecture? It is starting at slide 29 of week 2 lecture. That's where we're at. Awesome. So what is a histogram? Whoops, it helps I did that. Uh-oh. Technology. Oh, here's what I did. I'm back in my office in the basement, and now I have both my screens, so that's fine. We're going to make it work, except I don't want to be here, so can I just move that to, ooh, look at this, it's fancy. Okay, do you guys see the histogram? Is that what it says?
Yep.
Okay, so a histogram is a graph that shows the difference in frequency, or sometimes it'll be percentages, among categories of specifically interval ratio variables. This is not going to be for nominal data, right? We talked about bar graphs being better for nominal data. Histogram is for interval ratio variables. So you're going to see there, well, let me just show you instead of me using my fingers, that's not helpful. This is what it looks like. So the bars actually touch one another because as one category ends, the other one begins right away. Sorry, that's my dog. So the way that works is, for instance, this depicts age at death. There's no gap, right? So either you die at 20 or 21, right? Like the two have to touch each other. They're not going to be separate because they're on a continuous interval line, okay? So this is the way I would depict this information. Can you guys see my cursor, or can you see it now?
Yeah.
You see it now?
No, before.
Before, okay, weird. So why is that there? Anyway, it's fine. So this shows here, the mean is 60 years old, the median is 62, and the mode is 72, okay? And that's because you can see the greatest frequency is right here at this bar, that would be 72. And then if you were to take the mean, again, the average of this whole thing, you'd be a little, a little lower, obviously, because there's more data here, right at the 60 years old. And then the median is right at 62. Okay, so this is the statistics I can get from it. Okay. We talked about this already a little bit today. The shape of frequency distribution, and again, it's any sort of distribution of your data can take on a few ways. This is unimodal, like we talked about, so there's only one mode, and you can see it's right at this peak. Bimodal, meaning there's, two big peaks. And then there's also a rectangular distribution. This is fairly rare. That's if there is no data at each tail, you just start really, really high, right in the middle scores. That's more rare, but you can see what they look like, obviously. Okay, so symmetrical versus skewed distribution. We just talked about this again. So let's go to this next slide. This is how you would decide whether it is symmetrical and whether it is shows level of what's called kurtosis. Kurtosis is separate from skew because, as you can see, all three of those are actually symmetrical at the mean, right? You can flip, if you cut them in half and flip them together, they'd be identical. But they show different level of kurtosis, which means how evenly distributed the values are. If it's really, really skinny and it goes straight up, that's a really light tail, or a heavy tail, I should say, because it's heavy centrally, but a very light tail. So that means all the values are right in the middle, and then it drops way off. This, on the other hand, is light-tailed, and it's more of a flat distribution. That's almost more of the rectangular one we were looking at before. So that is what kurtosis specifically is, the deviation from a normal curve as far as how it's peaked and how it's flat. So those are two different pieces to that. Okay, so again, if we look here at the number of people in a toddler's play area based on age, you see that there's more here at the beginning. This is, again, kind of see, once they're really little, there's a lot in the area. Then they get to be older and they just run from each other. They're not around one another. And then they group play, they do pretend play and activities, so they group again together. So this would be a bimodal distribution. This would be more rectangular distribution. So that's the number of students per grade level. You're going to notice that there at no point, right, there's not going to be zeros. There's not going to be 0 student in first grade. It's all going to be about even at a similar number. Okay. Floor and ceiling effect. That's when you're looking at, let's see, how do I make small? A floor effect, like in this first one, is when it's not possible to get to a 0 value, right? So for this one, it's the number of families, number of children. It's not possible to have less than 0 children, right? You can't go further than that. A ceiling effect is it's not possible to have a score that's higher than 100%. So see how here you've got this ceiling effect. You can't keep going, okay? That's just something to be mindful of. Like, it's possible to get scores that go all the way to each edge of your distribution. And you just have to go back and think like, well, what is it I'm measuring? Does this make sense? And in both of those, you can see how that would make sense. Can't have negative kids. Can't have, I suppose you could have 105% if there's extra credit questions, but okay. A line graph, a little bit different than a histogram. It shows the difference in frequencies or sometimes percentages, depending on what you're measuring, among categories. And again, you're going to be looking at interval ratio, but they're going to be points rather than being bars for each that are going to be touching one another. It's going to be points on your graph, and then you're going to be connecting it. And the point represent the midpoint of that category. So to give you an example, here's the population in Japan that is age 65 and higher based on these years. So you can see in 2010 what it looked like and in 2014. So instead of having a bunch of bars go through here like a histogram, it's dots instead that are connecting each midpoint. So that's another way to represent data. A time series chart has to do when obviously time is of the essence. So it looks at the change in variables during different points in time. So it may be years or months, or it may also be percentages or rates on the other axis. Again, it all depends on what you're measuring. So as an example, here's the percentage of the total population, again, of 65 years and older. And then you see the different continents and then number of years, okay? So this is in 2010, you see where they are, 2030, 2050. So this is using a time series chart to predict trends in aging adults based on what we're seeing in terms of birth rates. And it compares them with different continents. So there's definitely a point in time where time series charts are helpful. They're helpful in predicting, but they can also be helpful in showing longitudinal data. If you have data from 2001, 2002, 2003, 2004, that's how you can categorize it and then have it go one or the other. That's a common one for unemployment rate. You probably have seen that, where you'll have all the years down at the bottom, and then it's a line graph showing what is the unemployment rate for each year. Okay, distortion. This is always my favorite, right? Let's insert a little bit of reality into that. So graphs are super helpful because they can quickly show you a very quick picture. But as we saw just earlier before the break, if you pay attention only to one part of the data, or somebody is trying to manipulate some of the data and just show you one section of it, it can greatly distort the actual information that was gathered in a specific study. So we need to be just very careful. So let's look at some distortions. So what do we consider graphical distortion, right? Can you guys think of an example where somebody could be distorting a graph? You're like, and Dr. Wolto, this is why we are taking this class. Please tell us all the ways.
I mean, if you look at a pie chart as we did before, and it gets a little muggy when it gets to like the 0.1%, and everything's like somewhat an off shade of green.
Right. So if you're presenting the information that makes it very hard to read at a first glance by using very similar shades of color, you're doing some sort of distortion so that people are not paying attention to that because it's hard to read. They're going to instead pick out the colors that stick out, right? Yep, absolutely. A few of the ways, if you're not using equal interval size, it may seem like one is much larger than the other. You can exaggerate proportions by changing the scale on your axes, right? Is it going to be by 1 or by 0.25? Well, now all of a sudden the difference is going to seem huge just because I adjusted the scale. Having a lack of information just in general, like a lie of omission, is another piece. So we need to just be very careful. So let's look at a few of these. This is a misleading illustration of a frequency distribution due to unequal interval size. Okay, so we take a look here. This is the commission payment to travel agents, and you see the different groups, the different airline groups, okay? And then what do we notice? Look at 50 to 57, the difference between these two, and 70 to 79. Anything strike you as odd?
70 to 79 is almost smaller.
Yeah. So how they outlined it is not accurate. And here we have 100 to 109, which is the same as 70 and 79, but look how much wider that is. Okay? So that's distorting data. That's not telling the full story. This is what I was just describing. Axes can be stretched or shrunk to create any result that they're interested in, okay? So let's take a look at that. So we have this one. This is the female representation in national parliament in 2015. So these are different countries, and this is the percentage of female, okay? So looking at that, let's look at the next one. What do we notice here? So here, it goes 0 to 70. Here, it's from 30 to 70. Does it look different when you look at it? I feel like this is like an optometrist appointment. Which one looks better? This one? This one. Like it's an incremental change, right? What do you guys notice? Anything? It seems to me like on this one, the difference is much larger, right? If I'm looking at Sweden and Mexico versus Rwanda, I'm like, man, they are forward thinkers. Look at that, the percentage of female versus here where, well, yeah, there's a difference, but it's all fairly close together. Okay, so something to be mindful of. That's another way to manipulate data. Here's another way. This is a misleading bar graph because you're not actually starting at 0. The vertical axis starts at 150,000 compared to 0 for this one, okay? So all of a sudden you could be like, whoa, people made way more money in 2008 than 2011, right? That's a huge difference when really if you look at it from a natural 0, which is what it should be, there is a dip, but it's not as significant, okay? This is a histogram that shows the student's stress rating distorted from a standard width to 1 to 1.5 times in height. Okay, so you can see the frequency here and the stress rating. And this is how, you see how they've like stretched it out? Does this seem more impressive? Like, whoa. They're really stressed out. Again, not that this does not indicate stress, but by stretching it, you're getting a visual information that says this is way worse. Okay, so here's another one. We've got data here, okay? Changes by 100. What's missing on here? I don't know about you, but that's meaning nothing to me. What are we looking at?
It didn't label its X or Y axis. It just says data and group.
Right. What are these groups? What are these numbers? We don't get any information. Okay. Now, this is exactly the same data. You guys see that? This is 9100 to 9800. So it's divided by 100s. Not at a natural 0. Here it is at a natural 0. Could you see any difference in this data? I mean, eyeballing it, you can be like, well, maybe group A is a little less, right?
Gotta get the ruler out.
Right, exactly. Okay. IQ as a function of gender. What is this graph telling us? You can say it. You won't get in trouble. This graph suggests.
Is it saying that males have higher IQs than women?
Right. Right. So any problem that you see with this graph?
It's by twos.
It's by twos. Now, the IQ score, is it possible to get a natural zero?
I don't think so.
So
I think you probably could, actually. It's very unlikely. So as to whether it should start at zero, maybe not, but having it be by 2-point increments, this shows a very large discrepancy compared to that. Right? Now you're like, well, actually, that's about the same. And then we'll talk about, again, the IQ score has a mean of 100, and we'll talk about standard deviation in coming weeks. Standard deviation of 15. So they are both within the same standard deviation. But if this is the information I'm presenting, that's telling a totally different story. Again, there's no manipulation of data. It's not like someone was like, I'm going to invent the fact that some guys have a 400 IQ. Nothing like that. It's just in displaying your graph, by changing some components of it, you're telling a very different story. You are misrepresenting, that word that I can't seem to say right now, in order to tell a particular story. Okay, so let's look at this one. Not starting at zero can have a huge effect on a graphical depiction. So here's at zero versus starting at a totally different point. Okay, you see the difference here? Like this is not highlighted in here. So now let's take it the flip side, right? This is probably not telling me a whole lot. This, in fact, is probably sharing more of the information, but you need to then provide a discussion that's reflective of that. Same here. This here is not very reflective of what's going on, but talking about the difference here, like this is probably, you see it says plus 20, because your total thing, like this would be dumb to graph it this way, right? Because your entire data set is between 20 and 20.45. Do you guys see that? So doing a graph starting at 0 to 25 tells us nothing. So this is not helpful. Okay? So it's important when you're thinking about how do I display the stats and the data that I'm gathering? How do I do that? You can look at different parts, but so these particular ones, they're good to display comparisons between groups. So like we looked at men and women earlier today and what they want in partners. You can show that with a bar chart very easily because you'll have one color bar that's for men, one color that's for female. Same with a line graph. You can have two different colored lines going through and displaying your data. Same with a time series. But a histogram is not good at that. Histogram is not good at comparing two groups. That's not the goal of it. So it's just good to know if I'm asking you, draw your data, don't pick a histogram if we're comparing groups. So why do we use charts and graphs? Well, oftentimes when you're just looking at a table, it is not clear what patterns, trends, or hypotheses can be derived from the data. It's just not. So a chart or a graph can be very useful in just displaying that information more quickly. You can also show more easily with a graph the relationship within the data. So again, displaying men and women, right? And the difference between that. That's much harder to do in a table. In fact, I would dare say that would get very clunky because you'd add different columns. It wouldn't be helpful. And then you can use, when you're working with charts, it is very easy to get caught up in all the minutia. Like, oh, what color should I use? And how should I format? And so again, if you're just gonna go with the chart angle, it should really not be just chart. It should be both, right? And here's some of the things that you do gain. What do you lose, right? And what do you gain? You can get your reader's attention immediately. You're able to focus on the larger picture rather than granular data, right? Looking at just one number in a table can make you lose sight of the forest for the trees. So it's easier if you end up displaying it via graph. Okay. So that's one of the reasons why it's helpful to use. So here's some key terms that are going to be helpful for you guys as you think through and prepare for future exams on that. Any questions about graphing, tables, and visual representation of data? Anything come to mind? Okay.
I don't think so.
So for the exam, you will be asked to create some graphs and tables. The problem with full online class is that it's going to be easy. Well, easy maybe is not the right term, but one of the ways that you can do that is by having your data written and then just saying insert chart or insert graph, right? Or insert pie chart. You can do it that way. My preference would be more for this kind of terrible writing where you're just doing it on your own. So I'm going to need to see how we can make that work as a class. I suspect I'll give options for both. Some of you that are like, I don't know how to manage the technology to make a pie chart or a histogram, that's totally fine. You can always utilize paper pencil. Like I said, you can take a picture, attach the picture as a PDF to your assignment, text it to me, email it to me. I will accept any and all of the above. But being able to graph and do a visual representation of data is going to be important to know. Okay, questions as we head into next week?
So the exam will be, sorry, I can't pull up the syllabus quick enough.
Let's see if I can do that. You're looking at the date, is that what you're wondering, Elizabeth?
Yeah.
The exam looks like it's October 14.
Okay. And then we will be able to look at like a study guide for that to where we can, or reviewing the key terms of each PowerPoint.
Reviewing the key terms, looking at your quizzes and the labs, that's going to give you insight also as to what you need to do. You guys, I think I still have a fall break on our schedule. Why did I do that? There is no fall break, right? October 21st?
No, I don't think so.
I don't know why I did that. Why did I do that? So I'll fix that. There's plenty of info to pass around. So yeah, but it looks like that's the date of our first exam. It'll be October 14th.
So will that be an exam that we do when we're in class or like have a break like we do the quizzes?
It's going to be the entire class session is
Okay.
going to be the exam. So I'm going to have it go live at the start of our class at 2 o'clock, and you will need to complete it before the class ends at 5 o'clock.
Okay.
If for whatever reason somebody's got a life event, something's going on, you need extra time, please do let me know if you need accommodations of any kind. I also need to know about that to make sure I make it fair. Or if something comes up, obviously people can let me know as need be. But otherwise it'll be between that period of time. So we'll all log on to a Zoom and I'll give you guys warning ahead of time. I'll give you any hints or questions you may have. And then during the exam, if you have any questions, I'll make it clear. I'll probably even writing on the test my phone number so you can text me and I can answer a question quickly.
Okay, and then so should we be prepared to be using like the numbers or Excel program for like pivot tables and stuff like
Yes,
that?
you should. Mm-hmm.
Okay.
I'm going to tell you now, there's not going to be another pivot table. So you're not going to be doing that, but you'll need to use some other statistical analysis. Yeah.
Perfect.
Okay.
Yeah, so it's going to be Z-scores and you'll need to do that in there.
Okay.
Giving away all the answers, you guys. No surprise on this test. Right. Any other questions? Check us out on time, 4:30. Please reach out if you have any questions. If you've not submitted your lab, please let me know. Send it to me at any time. We'll make that count and I will submit all of your grades as well by next week.
Awesome.
Thank you.
All right. You guys have a great day and let's talk again real soon.
You too.
Bye.
Bye.